Okay. So this is the trajectory planning and its types of the robots. Okay. Thank you. We will see in the next concept. Hi to everyone. MEM School of Engineering, Department of Mechatronics Engineering, online classes, subject robotics machine and vision system. So unit number 3, that is robot mechanics. So last class we discussed with the trajectory planning and its types. Now we are going to see about the dynamic model of manipulators. Already we know the direct dynamics, inverse dynamics. Okay, so that is study of the relation between the applied force and torque and the resulting motion of the industrial manipulator. That is called dynamic robot dynamics. So direct model is, that is direct dynamics. Once the force torque applied to the joints as well as the joint position and velocities are known, compute the joint acceleration. Okay, that is acceleration depend on the function of torque, position and velocity. This is the concept. Okay, this is the concept used in the direct dynamics. Okay, or forward dynamics. Okay, from that we can get the value. Okay, integration of acceleration will be velocity. Integration of velocity will be position. Okay, previous one we are using with the in forward and reverse kinematics we are using the what the value we are using the differentiation. Here we are using the integration. So inverse model, that is inverse dynamics. Once the joint acceleration, velocity and the positions are known, so compute the corresponding forces or torques. Okay, this is the reverse concept. Okay, that is we are calculating the torque value with the what position, velocity and acceleration. So this is a simple concept to understand the dynamic. If I are giving force like this, okay, if you are giving force like this, torque will be produced. Okay, that means if you are using the force 1 Newton, okay, the radius of the rod will be 1 meter, means it will produce the 1 Newton meter torque. So this is the relationship between the force and the torque. Okay, if you are using 1 Newton force means you will get the torque of 1 Newton meter. Okay, this is the normally a manipulator is composed by an open kinematic chain and its dynamic model is affected by several drawbacks: low rigidity, potentially unknown parameters, dynamic coupling, and arm lengths. Already we discussed. Okay, when dynamic model, there are two approaches they are using. Okay, first approach is Euler-Lagrange approach. Second one is Newton-Euler approach. So first approach to be developed by the Euler-Lagrange. The dynamic model obtained in this manner is simpler and more intuitive and also more suitable to understand the effects of changing in the mechanical parameters. The links are considered all together and the model is obtained analytically. So drawbacks of this one is the model is obtained starting from the kinetics and potential energies. The model is not computationally efficient, but based on the computationally efficient recursive technique that is exploit the series structure of an industrial manipulator. So on the other hand, the mathematical model is not explored in the closed form. This is the second concept we are using the Newton-Euler approach. Okay, first we need to know robot dynamics. Okay, that is static analysis. That is here we have same tooling forces, tooling robot arm, that is our here L1 and L2, same as torque 1 and torque 2 to the L1 and L2. Then first force F1 minus F2 is equal to 0. So F2 minus F is equal to 0. Then you will get the F1 and F1 is equal to F. Okay, T1 value. So like that we can calculate the T1 and T2 value. Then you will get the T2. From that we can get the Fx and Fy value. So this is the compensating gravity, because gravity will normally we can calculate the first value, but here we are considering the gravity because of using gravity also the force will be varying, torque will be varying. Okay, so we need to consider the gravity. So F2 is equal to m2g. Okay, we from that we can get the value T of values. Okay, so first Lagrange mechanism. So the Lagrange and L of any system is defined as L is equal to K minus B. So K is kinetic energy of the system, P is potential energy of the system. So Lagrange equation F is equal to d by dt of dot del dou of q dot of I minus dou L of q L divided by dou of qi. So F is generalized force coordinate, qi is generalized position coordinate, q dot is generalized velocity vector. Generalized velocity vector. So example of 2 DYF manipulator for the kinetic energy of the link n minus 1. That is K1 is equal to 1 divided by 2 M1 V1 square. M1 V1 square. Then V1 is equal to D1 omega 1 is equal to D1 of omega means angular. So that is velocity theta of 1. K1 value that is half mv square, that is half m1 d1 square theta dot square. So potential energy of the link. So P1 is equal to H1 is equal to P1. We can directly written. You know to write any format. We can directly know that. That is kinetic energy of link 2. So kinetic energy of link depend on the x2 and y2. See the value. X2 is equal to d1 of sine theta 1 plus d2 sine theta 1 plus theta 2. Y2 is equal to minus d1 cos theta 1 minus theta 2 cos theta 1 plus theta 2. So same as velocity x2 y2. Okay, so velocity square is equal to, you can get the square plus y square value using a trigonometric formula. You can reduce the concept. Okay, finally you get the k value. Then you will get the potential energy of the link P2 will be like this. Then apply this means you will get the value. So that is a Lagrange's kinetic and potential energy. K is equal to this one, K1 plus K2, P1 plus P2 is equal to K minus P. Okay, this is the concept. Okay, Lagrange L is equal to K minus P only. They are considering the kinetic energy and potential energy. Okay, so kinetic energy depend on the velocity and the mass. So our potential energy depend on the ground, that is gravity. Using gravity, it will produce the concept. This is the Lagrange concept. Okay, this is the basic concept of analyzing the dynamics model. Okay, thank you. So in this class, we will see the Newton-Euler formation of finite differential analyzing the dynamics method.